Polymer networks, structure, characterization, and emerging functionalities. Polymer networks are three-dimensional macromolecular architectures formed through covalent or reversible cross-linking of polymer chains, spanning materials from rigid thermosets to highly deformable hydrogels. Their macroscopic behavior is governed not only by the chemical composition of constituent strands and junctions but also by the statistical and topological complexity inherent to network formation. This video report presents a concise overview of polymer network structure, gelation, and characterization, with emphasis on recent advances in structural control, dynamic covalent chemistry, and molecule-to-material relationships. Emerging methodologies that bridge molecular scale behavior with bulk properties are discussed, highlighting opportunities to rationally design advanced functional materials. Polymer networks represent a fundamental class of materials characterized by interconnected macromolecular chains forming a continuous three-dimensional structure. These systems include elastomers, thermosets, and solvent-swollen gels, each distinguished by the nature and density of cross-links. Unlike linear polymers, polymer networks exhibit complex structural heterogeneity arising from stochastic cross-linking processes, leading to distributions in strand length, junction functionality, and network defects such as loops and dangling ends. This intrinsic disorder complicates the establishment of direct structure property relationships, limiting predictive material design. Recent developments in polymer chemistry aim to overcome these limitations through improved control of network architecture, incorporation of reversible chemistries, and advanced analytical techniques. In particular, strategies such as end-linking of well-defined precursors, dynamic covalent polymer networks, and interpenetrating architectures have significantly expanded the design space of polymer networks. Network formation and molecular architecture. Polymer networks are typically formed either by cross-linking pre-existing polymer chains or through the polymerization of multifunctional monomers. The resulting structure consists of polymer strands connected at junctions, where strands may act as elastically active bridges, form loops, or terminate as dangling ends. Junctions may be permanent, arising from covalent bonds or trapped entanglements, or reversible, resulting from supramolecular interactions or dynamic covalent linkages. The molecular architecture of precursor polymers plays a critical role in determining network uniformity. Conventional random cross-linking often produces highly heterogeneous networks, whereas controlled approaches, such as end-linking of star-shaped polymers, yield more homogeneous structures with narrower strand length distributions. For example, tetrafunctional polyethylene glycol, PEG, star polymers have been widely used to fabricate model hydrogels with well-defined mesh sizes and mechanical properties. Dynamic covalent polymer networks, DCPNs, introduce reversible bond formation into the network structure, enabling rearrangement under external stimuli. Chemistries such as imine exchange, disulfide metathesis, and Diels-Alder reactions allow networks to exhibit self-healing, recyclability, and shape memory behavior. These materials have found applications in soft robotics, additive manufacturing, and sustainable materials design. Gelation and network development. The transition from a viscous polymer solution to a solid-like network occurs at the gel point, where an infinite network spanning the entire system is formed. Below this threshold, all species remain soluble and can be characterized using conventional solution-based techniques. Above the gel point, the system separates into a cross-linked gel fraction and a soluble fraction, sol, consisting of unreacted chains and branched oligomers. Characterization of the gelation process is essential for understanding network formation. Techniques such as size exclusion chromatography, SEC, combined with light scattering enable analysis of molecular weight distributions approaching gelation. Socklet extraction is commonly employed to separate sol and gel fractions, allowing independent characterization of each component. The gel fraction can be quantified gravimetrically, while the sol fraction can be analyzed using spectroscopic and chromatographic methods. Swelling experiments provide further insight into network structure. When immersed in a suitable solvent, polymer networks absorb liquid and expand until equilibrium is reached. The equilibrium swelling ratio is directly related to the cross-link density and mesh size of the network, as described by Flory-Renner theory. For instance, lightly cross-linked polyacrylamide hydrogels exhibit high swelling ratios and large mesh sizes, making them suitable for drug delivery and tissue engineering applications. Characterization techniques. Comprehensive characterization of polymer networks requires a combination of analytical techniques spanning molecular, structural, and macroscopic scales. Spectroscopic methods such as nuclear magnetic resonance, NMR, and Fourier transform infrared, FTIR, spectroscopy are routinely used to determine chemical composition, functional group conversion, and network formation. NMR, in particular, provides detailed information on molecular structure and dynamics, including end-group analysis for molecular weight determination in precursor polymers. Size exclusion chromatography remains a cornerstone technique for evaluating molecular weight distributions of soluble components, while light scattering methods enable the determination of polymer size and conformation in solution. Mass spectrometry, particularly with soft ionization techniques such as MALDI and electrospray ionization, has further enhanced the ability to analyze complex polymer architectures. Thermal analysis techniques, including differential scanning calorimetry, DSC, are used to probe glass transition temperatures, crystallization behavior, and reaction kinetics. Rheological measurements are central to understanding the viscoelastic properties of polymer networks, providing insight into cross-link density, relaxation dynamics, and mechanical performance. At the nanoscale, advanced techniques such as atomic force microscopy, AFM, coupled infrared spectroscopy and single molecule force spectroscopy, SMFS, enable direct probing of local structure and mechanical behavior. SMFS, for example, has been used to measure force extension relationships of individual polymer chains and to investigate mechanochemical responses within networks. Network topology and structure property relationships. The topology of polymer networks, defined by the connectivity and spatial arrangement of strands and junctions, plays a critical role in determining material properties. Key parameters include cross-link functionality, degree of conversion, and the presence of structural defects such as loops and dangling ends. At larger length scales, entanglements and spatial inhomogeneities further influence mechanical behavior. Traditional methods for probing network topology rely on indirect approaches, such as fitting theoretical models to swelling or mechanical data. However, recent advances in solid-state NMR and network disassembly spectrometry have enabled more direct and quantitative analysis of network structure. These techniques provide new insights into the distribution of defects and their impact on material performance. Interpenetrating polymer networks, IPNs, and double network systems exemplify the importance of topology in enhancing mechanical properties. In double network hydrogels, a rigid, brittle network is interlaced with a soft, ductile network, resulting in materials with exceptional toughness and resilience. Such systems have been demonstrated in PAMPS, polyacrylamide hydrogels, which exhibit fracture energies orders of magnitude higher than conventional hydrogels. Emerging directions and applications. Recent progress in polymer network science has been driven by the integration of chemical reactivity into network structures. Mechanochemically active networks, incorporating force-responsive molecules, mechanophores, enable direct coupling between mechanical deformation and chemical transformations. This approach has facilitated the development of materials with stress sensing, self-strengthening, and adaptive properties. Dynamic covalent networks are also advancing sustainability by enabling reprocessable thermosets and recyclable materials. Vitrimers, for example, combine the mechanical robustness of thermosets with the reprocessability of thermoplastics through associative bond exchange mechanisms. Polymer networks are widely utilized across diverse applications, including protective coatings, automotive components, biomedical devices, and agricultural systems. Hydrogels are extensively employed in drug delivery and tissue engineering, while elastomeric networks are critical in flexible electronics and soft actuators. In conclusions, polymer networks are inherently complex materials whose properties emerge from a combination of chemical composition, molecular architecture, and topological organization. While traditional approaches have been limited by structural heterogeneity, recent advances in controlled synthesis, dynamic covalent chemistry, and high-resolution characterization are enabling unprecedented insight into network behavior. The ability to establish quantitative relationships between molecular-scale phenomena and macroscopic properties represents a transformative step toward rational design of polymer networks. Continued integration of experimental, theoretical, and computational approaches will be essential for unlocking the full potential of these versatile materials.